Welcome back to Muddy Math, where we take middle school math concepts that are a little muddy and clear them up. Today, we are talking about proportional relationships, and I hit the trails to think about walking, breathing, and stepping proportionally. So if you want to do this activity, you'll just need a way to collect data on counting your steps, how long it takes you to walk between two distances, and a way to counting your breaths. And if you'd like to download an app to determine how far you actually walk, or if you have a tape measure to figure out how far you actually need to walk, go for that. I recorded myself walking the trail, so I'm not sure how this is going to play using live stream, but this is just showing you that I actually did the activity and the results that I got. I'm going to walk, count my breaths between this yellow post and that yellow post. So, exhale, you get the point. So I'm walking between two designated spaces on a trail. I count how many breaths I take. I count how many steps I take, and I measure the time it takes me to walk between the two posts. I do this several times to collect a general idea of my speed, my average speed for these changing quantities. So the goal is to then graph these quantities on the XY plane. So you're going to choose a distance to walk, use a stopwatch, measure how long it takes you, do this several times, get the average. Step 3, walk the distance several times, each time counting your breaths and steps to find a typical number to represent the number of breaths and steps you take while walking the determined distance. Part 4, you can also try to measure the distance in meters or yards, like I said, using an application or some sort of measuring tool. And then you want to graph time on the x-axis. So you'll see here that, I don't know if you want to see my face or not. If I stand over here. Hey, okay. So while you're looking at the XY plane, you want to graph time on the x-axis. So you see that this is the x-axis, it's the horizontal axis, and that is where you should graph time. Time is typically our independent variable because it's not something we can control. Time is ongoing whether we like it or not. So I always interpret time as an independent variable, and then you can graph multiple changing quantities on that y-axis. It's really nice to graph multiple changing quantities on the same xy plane so that you can compare them. And today we're talking about proportional relationships. So really the only thing we can compare, since they're all going to be starting at the origin, is their rate of change. And that's the slant at which their graphs are growing. And these are all positive quantities because I'm talking about counting breaths, counting steps, and distance. Here's another XY plane you can use. Remember, the origin is a very key component in proportional relationships. They have to meet at the origin. So if you want to take a peek at what my trail walk looked like on the XY plane, this is it, okay? So you have the y-axis representing steps and breaths, okay? So when the XY plane is representing steps, you see that I'm taking many more steps than I am taking breaths. In 20 seconds, it took me 26 steps, but only 7 breaths. So it would make sense that I'm doing more steps than I am breaths. So the slope of the line representing steps is going to be much greater than the slope of the line representing breaths. And these are both proportional because I'm deciding that they're all starting at 0. My time, my breaths, and my steps are all 0. At 0 seconds, I've walked 0 steps and I've taken 0 breaths. Quick interpretation of these words linguistically, getting some definitions. A relationship is proportional if the quantity measured on the y-axis changes at a constant speed. As the x-axis, quantity increases. So I'm not getting faster, I'm not getting slower. It's changing at a constant speed. So it's a straight line, And if I was getting faster, it would scoot way, way, way up. If I was getting slower, it would kind of level out. And here they're straight lines. So these are linear relationships, but specifically they're proportional relationships because they're starting at the origin. I'm getting a warning from YouTube. Let me check what that is. Okay. Anyway. I hope in that break you got to think about these ideas. Whenever I take a break, please take that as an opportunity to reflect on what I've said. So if the point 0, 0 exists as a solution to the equation representing your two quantities, then it is proportional if it's changing at a constant rate of change. And that constant rate of change is known as many different things. It's known as a constant of proportionality, which is represented by this variable k. And when you think about this variable k, it's really what you're multiplying the number of time, the measure of seconds in this case, because x is representing time in seconds of me walking on the trail. If I multiply that by k, that'll tell me about the y value, the change in quantity on the y-axis. It's dependent. It's depending on time. So it makes sense for me to have to put time in, multiply it by a constant, k, to get the y value. This is different than all linear expressions, because not all linear expressions can you just multiply the time to get the breaths or the steps. When a relationship is linear but not proportional, it's typically represented with this formula, y equals mx plus b. In the case of proportional relationships, b is 0. So we just drop it. So you'll see here y equals kx plus 0. There's no reason for us to say plus 0. We're telling you that because it's proportional, it's starting at 0, so we don't need to write plus b. Now, these are all beautiful proportional relationships shooting out of the origin because they're starting at 0, 0. Okay? If something is proportional, okay, k is the letter used to represent slope. If it's not proportional, then the letter used to represent slope is m. They're just letters. Don't be afraid of them. Don't worry about them. The important thing is in a proportional relationship, you can just multiply the independent variable by a single value, a factor, and get the dependent variable. In other linear expressions, you have to multiply and then add. For proportional relationships, you just have to multiply. Okay, so we're going to continue on with some vocab here. Linear relationships can be represented by an equation of the form y equals mx plus b, where m is the speed of the y value changing as the x value changes by 1. And b is the starting value of y when x is 0. Okay? Both quantities must measure initially at 0 to be proportional. Proportional relationships can be represented by an equation of the form y equals kx plus 0, where k is the speed of the y value as it's changing as the x value changes by 1. Y equals kx. These are proportional relationships. Okay? I hope that this repetitiveness of the vocab words is helpful in you differentiating why we learn about proportional relationships and why we learn about linear relationships. Proportional relationships are a type of linear relationship. And in this case, when I'm walking, I'm saying time starts at 0, breaths start with 0, and steps start with 0. I count 20 seconds about on average for my distance to walk between the two posts. I take about 26 steps and 7 breaths. So these are the table of values, the graphics, I like the graphical representations, the table of values, some numeric representations. Algebraic representations are right here, y equals 1.3x and y equals 0.35x. That's because the value of 7 divided by 20, I'm measuring in seconds here, 7 divided by 20 is exactly 3500ths, and 26 divided by 20 is 1.3. So these are where I'm getting my slopes. How do I graph that? You can plot points. So you see here is the point 1013 and the point 2026. So these represent steps and time. And then for my breaths line, I just plotted the 7 breaths at 20 seconds. Then I draw a line through the origin, through that point, and I get my graph. The steepness of that line lets me know comparatively which one's faster. So the red line is steeper, so it's faster than the green line because I'm taking more steps than breaths. These scales on my X and Y axes are not the same. So this is a little deceiving because typically a slope of 1 will have a 45-degree angle to the x-axis if the X and Y axis are labeled at the same increment. So here they're not labeled at the same increment, so it's skewed. It's a skewed picture. It's not a proportional graph. In the PDF enhancement, I've given you a blank organizer to help you graph your walking, stepping, and breathing. You can access this in the link below, in the description below. Okay, and then there's this challenge. If you'd like to take the challenge, translating proportional to be non-proportional. So let's see my pre-recorded adventure on the trails and see what happens as I talk about translating my graph so it's no longer proportional but still linear. So go to 4 minutes and 33 seconds. Remember, when I take a break, that's a good time for you to stop and reflect. Does that make sense to me? Now, how can we translate this story a little bit so that two quantities, breaths over time, does not intersect the y-axis at 0? The starting point for the y value is not 0. How can we adjust the story? I like that. So, how can we adjust the story? I was thinking we could adjust the story by thinking about our line as a movement up, down, left, and right. So if we look at our graph of breathing, okay, you'll see that if we translated the graph, now in this case, I like that you brought that up. Good question. So you'll see here it says y equals 21x instead of y equals 7 over 20x, because 7 over 20 tells me my number of breaths per 20 seconds. If I multiply 7 and 20 by 3, I get 21 over 60. 21 breaths over 60 seconds. What is equal to 60 seconds? That's right, 1 minute. Okay, so 21x becomes a representation of my breaths per minute rather than breaths per second, which I think makes more sense because every second I'm only taking a part of an inhale or an exhale, whereas every minute I'm taking 21 breaths. So here we go. We have a graph that, again, the intervals on the y-axis are different from the x. The x-axis is going from 0 to 10 seconds to 20 seconds. So you'll see I used that 7 over 20 to graph my line. In 20 seconds, I took 7 breaths. But I'm thinking about each of these as a second. So if I continued this line out, it would hit the point 60-21. And in terms of my slope, I want to think about the 21 breaths I'm taking in those 60 seconds, which is 1 minute. So this equation represents my changing quantities in breaths per minute. Now, if I translate this graph downward, you'll see it no longer intersects the origin. It's not intersecting the origin, it's not proportional, but it is still linear because it has a straight line, so it has a constant speed. Because I'm still breathing at 21 breaths per minute, but the number of breaths is starting at negative 3.5 instead of at 0. So instead of at 0 seconds, I took 0 breaths. At 0 seconds, I took negative 3.5 breaths. How can I take a negative breath? I mean, I was counting breaths as a full inhale and exhale. If I only inhaled, that's a half a breath. If I only exhaled a little bit, that's 3/4 of a breath maybe. So here I have a situation where I have a narrative based on the changing quantities on the XY plane, but it doesn't make entirely so much sense. How can you take negative 3.5 breaths? So this is kind of questions that mathematicians like to ask. Does this model represent my story? Does this make sense? Is this appropriate? Is this an appropriate equation? Do I need to say this is the equation when y is greater than 0, or y is greater than or equal to 0? Is this my equation for when the graph is only above the x-axis here? I don't know. So what do you think it means to you, having negative breadths, starting at negative breadths? You'll notice that once I have negative breadths, my graph intersects the x-axis at 10 seconds. So at 10 seconds, I've had 0 breadths. Negative 3.5 breadths might mean the number of breaths I take before I reach my first yellow marker. I'm still breathing. Maybe this is just going back in time a little bit. Maybe really thinking about 10 seconds being the starting point of me collecting data means that I'm walking up to the yellow hiking trail marker, and then, okay, it took me 10 seconds to get there. I took 3.5 breaths before I got to the trail marker, and now I'm at the trail marker at 10 seconds, and I'm beginning to breathe when it counts. I don't know. What do you think? Does that make sense to you? Please let me know in the comments below how your breathing rates and stepping rates compare to mine. Are you breathing more than 21 breaths per minute or less? How do you know? Are you walking or stepping at a rate that's faster than me? How do you know? Just as a reminder, my breaths per minute is 21, and if I multiply 26 by 3 as well, that tells me the number of steps per minute. 26 times 3, this is a nice number talk we can end with. Go ahead and think about, how would you do 26 times 3? Why are we multiplying it by 3 anyway? Oh, right, because I took 26 steps in 20 seconds. So to get my rate of steps per minute, I would multiply both steps and seconds by 3. It's an equivalent ratio or rate of steps to time. Okay, I've given you enough time, I think. If not, press pause and then check back in. But what is 26 times 3? How could you do it? My instincts tell me to do 6 times 3 is 18. Hold on to that 18. 20 times 3, well, let me just think about 2 times 3 is 6, add back that 0. 20 times 3 is 60. Bring that 18 back in from my cloud, and I have 60 plus 18 is 78. 78 steps per minute. Are you walking faster or slower than me? Please comment in the section below. Okay, check out the description for the PDF enhancement. I hope I got it right for you all. Get outside in the beautiful sunshine. Strengthen your vitamin D. Enjoy the sunshine. And I really encourage you to take every opportunity you can to enjoy thinking mathematically. Because if you enjoy it, you'll come back to it, and it's something you can grow and you can be proud of. And even if you're learning outside of a classroom, it's a powerful strategy and a powerful life skill to be able to commit to learning that is in your own hands and something you love. So I believe that you can love math. You have to just find the way that it fits into your life in a way that you enjoy. And maybe it's by taking some walks in nature and thinking proportionally. Thanks for tuning in. It's always, always, always a pleasure to bring some low-tech activities to your life so that you can get muddy in middle school math, clear it up, and then